Hi team, we are now starting sequences and their notations. Number one, we want to talk about what a sequence is. Sequence is a function, we'll just like if we use f of x, we can use a of x, whose domain is the set of natural numbers or positive integers. Think of it like the counting numbers, 1, 2, 3, 4. And this function produces a pattern. So the terms of the sequence are the function values, a when you plug in 1, function a when you plug in 2, function a when you plug in 3, and so forth. When we're referencing the terms in the sequence, we usually write a to the n instead of the function notation a of n. So the terms of the sequence are written as a sub 1 is the first term, a sub 2 the second term. A sub n just means some general nth term. So if we're looking at this example here, notice this pattern, 2, 4, 6, 8, they're even numbers. You have the little 3 dots, the ellipses there to 2n. That's really what our function looks like. 2 times some positive integer n. So 2 would be considered the first term. This would be our a sub 1 is 2. Our a sub 2 is 4. Our a sub 3 is 6, and so forth. So a sequence that continues indefinitely is called an infinite sequence. A sequence that is defined only for the first n positive integers is called a finite sequence. In other words, there's an end to it. There are typically 2 types of formulas for these sequences. The first one is called an explicit formula. What that means is we can go directly to the nth term, okay, using the position. If I want to know what is the 25th term in the sequence, I could plug in the n directly and I can get my 25th term. Another type of formula is called a recursive formula. And that's a formula where every term is defined by a term before it. So we always have to know the initial term or terms of that sequence in order to determine what the next number is. For example, we have this sequence of 5, 10, 15, 20, 25. They're giving us the first 5 terms. Well, we know they're multiples of 5. So the explicit formula is given that any nth term is 5 times n. So notice the third term, 15, is 5 times 3. The 5th term is 5 times 5. That means the 6th term would be 5 times 6, or 30. So we can go all the way out to the 100th term. We know automatically the 100th term would be 500. The recursive formula states that our first term is 5, but then any term after that is the previous term plus 5. So notice how that's represented. If I want to know the nth term, this here represents the term before it. So I would have to know if the 6th term is 30, then I would add 5 to it to get the 7th term, that would be 35. The nice thing about the recursive formula, it has to give you at least the first term, but I can't go directly to the 100th term. I would have to find 1, then 2, all the way up to 99 in order to find the 100th. We also have a new term called a factorial. N factorial is written as n to the exclamation mark, so that's read as n factorial. And it's the product of all the consecutive positive integers from 1 to n. So here it would say n factorial, we would multiply n times the number before that, times the number before that, all the way down to 1. A quick example is if we had 5 factorial, that means we would take 5 times 4 times 3 times 2 times 1, which would give us 120. Something that is important to note is 0 factorial has been defined as 1. It's used a lot actually in statistics and probability, which is why they've had to define that 0 based on some of our formulas as being 1. But let me show you where that is in your calculator. So as you remember, I said that it's used a lot in probability. So in order to put in 5 factorial, we put in the number 5, go to math, but notice up here at the top, we have numbers, complex numbers, probability. Some of you may have fractions or not, but scroll over to probability and you'll see that exclamation mark of 4. Hit enter to put it in and hit enter again, and it automatically gives you the 120. So again, that's under math, probability, and then you find your factorial. So in example 1, each sequence is explicitly defined. In other words, it's giving us a formula where we can go directly to the nth term. You want to write the first 3 terms and then skip to the 30th term of each sequence. So for example A, in order to find the first term, we plug in 1 everywhere there's an n. It's a plug and chug. So our first term is a -1/2. Our second term, we plug in a 2 for n, and we get a positive 1/4. Plug in a 3 for n, we get a -1/8. Before we jump to 30, I want you to notice that our sequence here alternates signs. It goes from -1/2 to a positive 1/4 to a -1/8. This -1 to the power of n is one way of getting that oscillating sign, those alternating signs. If you want it negative, you can do -1 to the n. If you start with a negative, if you want to start with a positive, you could do -1 to the n-1 or n+1. Now let's get down to the 30th term. -1 to the 30th divided by 2 to the 30th. Well, again, -1 to an even exponent is going to give us a positive 1. And 2 to the 30th is pretty large. Normally, I would just have you leave it as 2 to the 30th power. But if you were to multiply it out, I've already written it out here. It is 1,073,741,820 But again, I'm fine if you have an exponent that large to just go ahead and leave it as 2 to the 30th. Part B is a little bit different because it's given to us as a piecewise function, but that's fine. Our instructions is if it's an odd term, then we use that top portion. If it's an even term, we use the bottom portion. B sub 1, our first term is odd, so we're going to use that top formula. You will have 1 minus 1 factorial divided by 3. Remember, 0 factorial is defined as 1, so we get a 1/3. And if you forget, you can put 0 factorial in your calculator. It will give you a 1. B sub 2, our second term, so it's even. So we're going to use that second piece, 2 times 2 cubed. Please, please, please do not forget your order of operations. We have to cube the 2 before we multiply by the 2. So 2 cubed is 8, and that gives us a 16. B sub 3 is an odd term, so we're going to use the top one. This time plugging in 3, so 3 minus 1 quantity factorial divided by 3. We get 2 factorial divided by 3. 2 times 1 is 2. So we get a 2/3. We can also jump down to the 30th term. And again, 30 is even, so we use the bottom. 2 times 30 cubed. So that's going to give us 2 times 27,000, which equals 54,000. Our last example gives us a recursively defined formula, which again means that we have to know the term before it. And we want to write the first 3 terms of the sequence. Notice that they had to give us the first term in order to start. So even though it said the first 3, let's go ahead and do the first 4 so we can get the practice, because A sub 1 is given to us. So we know A sub 1 is 1. To find A sub 2, we would have 3 times. So notice you could plug in that 2 for your n plus 2, which means 3 times a sub 1 plus 2. A sub 1 is 1. So we get 3 times 1 plus 2. We get 3 times 3, which gives us 9. So again, this n minus 1 just means the term before it. So a sub 3, the third term, would be 3 times a sub 3 minus 1 plus 2, which equals 3 times a sub 2. So again, we're looking for a sub 3, so we got to use a sub 2 plus 2, which gives us 3 times, this time 9 plus 2. 3 times 11, which is 33. So notice how we knew a sub 1, so we used a sub 1. We knew a sub 2 was 9. Here we plugged in 9. So we're using that previous value. Just one more for good measure. 3 times a sub 4 minus 1 plus 2 means we're looking at 3 times a sub 3 plus 2, the previous term. Our previous term was 33, so we plug in 33 plus 2. We get 3 times 35, which gives us 105. So that's the difference between the recursive formula, where you have to know the term before it, or possibly 2 terms before it if it puts n minus 2. Okay, but again, they have to give you enough terms in order to satisfy the definition in that formula. Now we'll look at 2 specific types, arithmetic and geometric sequences. They're just 2 different types of sequences, one based more on linear addition and subtraction, and one more like an exponential where you're multiplying. So first of all, we got the arithmetic. And an arithmetic sequence is a sequence that the difference between any 2 consecutive terms is constant. When I would add to that, we add or subtract to get to the next term. So if we start with the first term, a sub 1, we call D the common difference of the sequence. So the nth term of an arithmetic sequence with a common difference D, you could take any term and subtract the term before it. So an explicit formula for the arithmetic for any nth term is the first term plus the difference times n minus 1. The recursive formula, remember that's the one that's dependent on a previous term, is the previous term plus that difference. And again, for this one, the n has to be greater than or equal to 2. The second type is a geometric. A geometric sequence is a sequence that the quotient, okay, so we're multiplying or dividing. A quotient between any 2 consecutive terms is constant. So we multiply or divide to get to the next term. So if we have the first term A1, we're going to use R to represent the common ratio. And to find that ratio, we would take any term and divide it by the term before it. So the explicit formula for a geometric is the nth term would be the first term times r to the n minus 1. Notice how that looks like an exponential. You have your initial value in the front, and you have that ratio or the rate at which it's growing to the exponent. Recursive formula is the ratio times the term before it. But again, we have to start with a term greater than or equal to 2. You have to have at least the first term. So again, notice the difference between arithmetic and geometric. The arithmetic explicit formula is a linear equation. Okay, it's a linear equation, whereas the geometric is an exponential. So let's look at some examples. So we want to write an explicit formula for the nth term of each sequence, which means we first have to determine, is it a pattern that is either linear, you're adding or subtracting the same number every time, Or is it exponential, where you're multiplying or dividing by the same number every time? So if we focus on A, we seem to be subtracting 5 every time. So that means we have a common difference of -5. You could take any term, subtract the number before it, 60 minus 65, -5. So our explicit formula is going to be the initial value of 75. That's where we're starting, minus that difference of 5 times n minus 1. So what does that mean if we were to reduce this? 75, distribute that -5, we get a -5n plus 5. So we would get an 80 minus 5n. So that would be our nth term. So notice that common difference is like our slope, right? It is decreasing by 5 every single time. If it was increasing, then it would be a +5. Now let's look at B. How is B changing every time? Well, we don't seem to be adding or subtracting, right? We're going from a 2 down to a 1/3, to a 1/18, to a 1/08. So if you can't see how it's getting from one term to the next, remember to find the ratio. We could take any term and divide by the term before it. So let's say if we took the 1/3 and divided by the 2, that would give us a 1/6 as our common ratio. And we can double check it. From here to here, we multiply by a 1/6. Here to here, 1/3 times 1/6 gives us a 1/18. And an 18 times 6 gives us a 108. So we are multiplying by 1/6 every single time. Our recursive formula is our first term, 2, times that common ratio of 1/6 to the power of n minus 1. And that's as far as we can go. That's our formula. Now let's take a look at C. This one's a little bit different. Notice it alternates signs. If it alternates signs, then it's not going to be arithmetic. Now, that doesn't mean it can't go from positive terms to negative or negative to positive. You can add or subtract where it eventually changes signs. But notice it goes from a -1/2, +3/4, -5/6, +7/8. They're alternating. It could be geometric. We would have to look and see. So we can choose any term, like a -5/6. And let's divide it by the term before it, 3/4. We can write it out the old-fashioned way if that helps, times 4/3. And that would give us 20/18, which reduces to 10/9. But in order for that to be a common ratio, that has to be the same ratio between any two consecutive terms. So let's try it again using 7/8 and 5/6. And that reduces to a -21/20. Those ratios are not the same. So different ratios, not geometric. But that doesn't mean we can't figure out what this formula is. So we do know that there's an alternating sign. So remember before when we had that alternating sign where the first guy was negative, we just have a -1 to the n. Just multiplying by that every single time will flip-flop the signs for us. Now we got to figure out what kind of pattern is going on. Well, even though the whole piece isn't arithmetic, let's look at the numerators and the denominators separately. 1, 3, 5, 7. What's happening with those numbers? Notice they're all odd, which in itself is arithmetic. You're adding 2 every time to the top. So we can write the top of that fraction as an arithmetic. The first term is 1. Again, remember that -1 in the front. We'll deal with the flipping of the sign. So we're only looking at the numerator itself. So our first term is 1. We are increasing by a difference of 2 every single time times n minus 1. So the top is arithmetic. Now let's take a look at the bottom. 2, 4, 6, 8. Again, it's increasing by 2 every single time we add 2, add 2, add 2. So the bottom is also arithmetic. It just starts with a different number. So the bottom starts with 2. It is still increasing by 2 every time. That's our common difference times n minus 1. So now we can actually simplify what's inside the brackets. We still have -1 to the n on the outside. We get 1, distribute the 2, we get 2n minus 2 on top, and then 2 plus 2n minus 2 in the denominator. -1 to the n with 2n minus 1 on top divided by 2n in the denominator. That in itself is an explicit formula, but we can keep simplifying it. -1 to the n. If we reduce those two, we would get 1 minus 1 over 2n. We can even distribute that -1 to the n if we wanted to. That would give us -1 to the n minus -1 to the n over 2n, or vice versa. All of those work. This one, this one, this one, all of them are considered explicit formulas for a sub n. In example 2, they want us to find the first term, a sub 1, of an arithmetic sequence, but they're giving us 2 values of that sequence, okay? So a couple of hints. First of all, they're telling us that it's arithmetic. If they only gave us 2 random points, we wouldn't know if it's arithmetic, geometric, or neither. So they would have to give us that information, and we know that formula. A sub n is a sub 1 plus the common difference times n minus 1. And so when you're approaching this problem, let's assume that you've never seen an example like this before. All you know, it's arithmetic, and you know what that formula looks like. So let's look at both pieces of information that they gave us. The first point, a sub 7 equals 21. What information does that tell us? That tells us that term 7, where n equals 7, that output value, a sub n, is 21. Okay, so if we focus just on that point, that would give us one equation. We plugged it in where 21 equals our first term, which we don't know, plus the common difference, which we don't know, but we do know the n of 7 minus 1. If we simplified that, that would give us 21 equals our first term plus 6d. Okay, so that gives us at least an equation, but we still have 2 unknowns. So this might lead you towards the next step, thinking one equation with 2 unknowns, but in order to solve that, I have to have 2 equations with 2 unknowns. That's where the second point comes in. This second point over here to the right tells us that when we're at the 15th term, or n equals 15, our output value, a sub n, is 42. So that can actually give us a second value. So if we had an equation B, where our output is 42, we still don't know our first term, we still don't know our common difference, but our n is 15. So we have 15 minus 1. We simplify that, we get 42 equals our first term plus 14d. Now we have 2 equations with 2 unknowns. That's why we learned system of equations before we did sequences and series. Notice everything builds. So let's solve this system of linear equations. So equation A, again, we have 21 equals our first term plus 6d. Equation B looks the same, so we can actually reduce our A1s. If we multiplied equation B by a -1, so that would give us a -42 equals a negative a sub 1 minus 14d. Combining like terms, we get a -21 equals the a sub 1s add up to 0, and we get a 8D. If only we'd gotten a -7, that would have turned out nicely, but we can still do it. We're pre-calculus students. We can work with fractions. So that gives us a common difference of a positive 21/8. But remember, they asked us to find the first term, a sub 1. So let's plug this back into one of our first equations. If we plug in this common difference into equation A, we would get 21 equals our first term plus 6 times 21/8. So we get 21 equals a sub 1 plus 6 times 21/8 reduces to 63/4. So let's rewrite this 21 here as a fraction over 4. So that would be what, 84/4 minus 63/4 would be our first term. So 84 minus the 63 would give us 21/4 as our first term. And that's what they're actually asking us for. We can always check it by putting it into equation B just to make sure that it works. Equation B, we want to see if it does in fact equal 42. So we had 21/4 as our A1 plus 14 times 21/8, which is our D. So we get 21/4 plus 14 times 21/8 reduces to 147/4, which is 168/4, which does in fact reduce to 42. So we found our first term. Example 3, we're supposed to find the number of terms for a geometric sequence. So again, they're telling us it's geometric. So that tells us that a sub n is our first term times some common ratio to the n minus 1. And this time, instead of giving us 2 points, they're giving us this sequence. And again, it's not just finding the formula, it's they want to know how many terms. So they gave us the first term, the second term, the third term, but they're saying this is a finite sequence and they want to know what is n. In other words, which term is the 2,187? It would be helpful if we knew what the R was. Well, given that it's geometric, we only have to check once. You might be able to tell multiplying the -1 times what would give us a +3. -3. So here times here, if we multiply by a -3, from here to here, if we multiplied by a -3, and we can also check it. The ratio equals any term divided by the term before it. We're going to get a -3. So in our formula to the left, we know not only the first term that was given to us, correct? -1, we know the common ratio, which is -3 to the n minus 1. So now we have the formula for the sequence. We have to find n. Well, we know a sub n. We know that entire term is 2,187. That's our last term in the sequence. We just want to know what's n. What number term is that? So that means we have to solve for our n. Now again, order of operations. I see too many people making the common error of multiplying the -1 by the -3 first. Remember, we can't do that. Go back to the pre-algebra stuff, which I know you know, but sometimes when we get to pre-calc and calc, we kind of forget some of the nitty-gritty fundamentals. So let's divide by that -1. So we'll get a -2,187 equals a -3 to the n minus 1. All right, so now in order for us to be able to solve this, it's an exponential. So we need to look at either seeing if we can get them into the same base or see if we can work with logarithms. Since we have negative numbers here, I would prefer to look at 2187 to see if that is some 3 to some power. Otherwise, we're going to have to play around with the signs a little bit to change it to deal with the fact that we have negatives and then working with a logarithm. So we can write 2187 as -3 to the 7th, okay? Use your calculator here. This isn't like, oh, obviously 3 to the 7th is 2187. Use your calculator, go, okay, 3 to the 5th, 3 to the 6th, or break down 2187. See how many 3's there are. So we get -3 to the n minus 1. So that tells us that if the bases are the same, then our exponents must also be equal. So we get n equals 8. If you're going to work it as a logarithm, however, we cannot use 2187 and -3, okay? We would have to use just the positive versions of both of those numbers. And I know that seems like, how can you do that? You can't divide by that negative because you got n minus 1. Don't think of it as far as us dividing by any negatives or negative ones or anything like that. We are merely looking to see what number that n could be that would give us a 287. Because remember, it oscillates. We're just looking for the n. So if you put that negative in your calculator and try to take a logarithm, you're going to get an error. So if we're just looking for that n, okay, we would just consider this to find what that n is. So we could take the logarithm of the left, 2187, and then the log of the right, 3 to the n minus 1. That allows us to move that entire exponent to the front. So we would get n minus 1 equals the log of 2187 divided by the log of 3, which is actually 7. If you put it in your calculator, add 1 to both sides, and we also get n equals 8. So again, let me stress, I want you guys to pay attention. What we did on the right-hand side, we did not divide by the -1. We did not divide by the negative of the 3, otherwise the 2187 would become negative. All we did is we said, okay, we want to solve this equation. In order to get an exponent out of the exponent position, we would take the logarithm or put them in like bases. But if you saw the logarithm, it is a valid approach. But the negative bases on both sides there would cause us trouble. But if 3 to some power would give us that -3 would give us this negative number, well, that absolute value should give us the same absolute value on the other side. So we didn't do anything mathematically to get rid of those negatives. We used our analysis skills to go, but the value of n should be the same even if they were positive. Okay, that absolute value would be the same. So we're just wanting to know which term it is. And either way, we found that term to be 8. Okay, so if the logarithm part throws you off, don't worry about it. You do the like bases method on the left. And that is it. That is it. We've got one more section, folks. One more. We can do this. All right. Talk to you soon. Bye.